Oftentimes, to do thermodynamic calculations, we rely on experimental data that has been collected by previous scientists and tabulated in books or databases. You may recall your instructor in organic chemistry talking about the strength of the carbon-carbon bond or the heat of some combustion reaction. You may also recall hearing your general chemistry instructor discussing the magnitude of latent heat of vaporization or the latent heat of fusion for noble elements, making the case that their magnitude reflects the strength of interamic interactions. In all cases, specific values were given for each of these physical properties. Do these physical properties have the same magnitude, regardless of the experimental conditions of temperature, pressure, purity, amount of material considered? No, they do not. So it is important for everybody to be aware of the specific conditions under which these physical properties are quoted. This is why scientists have emphasized the concept of standard state. This state specifies the conditions under which a certain property has that specific magnitude. So, what is the standard state of a substance? A substance in its standard state is assumed to be pure. It is assumed to be present in the amount of 1 mole. It is expected to be under a pressure of 1 bar, which we call the standard pressure. However, the temperature is not specified by the standard state, which means that we can have water in the standard state at 40 degrees Fahrenheit or water in the standard state at 80 degrees Fahrenheit. So, to fully describe the conditions under which the properties of a substance are reported in the standard state, we also need to specify the temperature. A common temperature used to report thermodynamic data for pure substances is 25.00 degrees Celsius or 298.15 Kelvin. It is also important to remember and not be confused by the fact that the substance of interest does not need to be stable under the standard state conditions used to report its properties. For example, water vapor at 25 degrees Celsius or 298 Kelvin is not stable. Water under these conditions is in the liquid state in its stable form. But we can still report the properties of water vapor at 25 degrees Celsius and 1 bar. The same would apply to atomic hydrogen gas. The stable form for hydrogen under these conditions at 298 Kelvin is H2 gas. So, what is a phase? A phase is a state of matter of uniform composition and properties. When you consider any substance, you can expect that they will have at most one vapor phase. Some substances, especially these of high molar mass, cannot be brought up in that state without undergoing chemical degradation, that is, without breaking covalent bonds. That is why you should not expect to hear anything about the physical properties of DNA or polyethylene in the vapor phase. All substances except helium exhibit a single liquid phase. Many, if not most, substances can exist in different crystal phase. We said that such substances exhibit polymorphism, or substance is a polymorphic substance. We will often talk about phase transitions. The word transition is sometimes substituted by the word transformation or change. A phase transition is simply the transformation of a substance from one phase into another phase. A well-known example is the vaporization of water. That is the transformation of water liquid to water vapor, which we write using the same formalism as we routinely use for chemical reactions. We will always assume that such phase change can take place under constant temperature and constant pressure conditions. In our example, this implies that water in a liquid state at the beginning of the phase change is at the same temperature and pressure as water in the vapor state at the end of the phase change. Phase changes, like chemical reactions, have associated changes in energy and enthalpy. That should not be surprising, since as a result of phase change, the molecules, or atoms for atomic substances, end up either further away or closer together in the final state than the initial state. We learned in a fundamentals chapter that the potential energy associated with intermolecular interactions is a strong function of the distance between molecules. So phase changes of the type encountered in this class always have non-zero energy and enthalpy changes. In the previous chapter, we said that delta U for the isothermal compression or expansion of an ideal gas was equal to 0. Obviously, this is a very different situation than the one encountered in a phase change, because in contrast with ideal gases, for which the energy only depends on temperature, whenever we are dealing with liquids and solids, we cannot ignore intermolecular interactions. The energy of liquids and solids therefore depends on both temperature and volume. So we will talk about standard energy changes for vaporization of liquid water, written symbolically as delta VAP U standard for H2O liquid. The subscript VAP is written to indicate that we are referring to the vaporization process. The subscript 0 is used to indicate we are referring to the value of delta U measured or calculated under standard conditions. We will also talk about delta cond H standard for H2O vapor, where the subscript cond refers to the condensation, the transformation of a substance from the vapor state to the liquid state.